This is actually the most interesting part. Okay, so did I start recording? Yeah. Okay.
So in a certain sense, it's probably like the thing you were maybe waiting for.
Yes.
But let me say, I mean, I'm not. So there is no exercise session today, so it's just me talking until you get bored. So
8 p.m. 8 p.m.
8 p.m. Well, depends on your attention span, I guess. So or until I fall asleep. But let me just say, so what I want to explain in some detail is how to fix the construction of modular integrals from yesterday. So there was just from last time. I explained how how to reduce Fourier interpolation formula of certain specific type for square root n. Kind of that's roughly what the formula looks like. So you can deduce that formula if you can show existence of modular integrals for the group gamma 2, and that was basically done by result of Knopp. So theorem of Martin Knopp. So that implied the existence of modular integrals. However, the proof that he gave is not that useful if you want to actually do something with the functions themselves. And we actually do want to do that. So there's two things that I really want to say from the actual, like the mathematical side without any speculations. So first I'll explain what is the substitute for his proof to make things computable in the. So first I'll treat the Stoy case of square root n. Then I'll explain how you make it work for the actual formula we use for universal optimality, and then I will tell like what. So how badly things fail and what's missing for the A2 story. At least some guesses about what's missing.
Thanks.
Oh, I'm sorry. Yeah.
I should have not enough to work.
Okay. So how to fix alternative proofs of existence or so different constructions of modular integrals. I will be a little bit, well, I'll just sketch a few of the approaches because they're useful for different things. So there's one approach that a student of Marina found. So you change the construction of the Poincare series in a way that you don't have to raise the weight, then divide through by Eisenstein series. So you can change it in a non-trivial way that actually directly gives you a solution to this modular integral problem. And yeah, just let me get that. So this is a student of Marina, Martin Stoller. So what's the idea? Well, it's actually very tricky. I mean, I can write you the formula, the solution, but to explain why it works, it requires a little bit of combinatorics. So we want solutions to this system of equations. So this is completely abstract version. So I mean, this phi actually will be something involving Gaussians, but for the method doesn't matter. And this kind of I'm using maybe a notation that I haven't quite explained. So this is not a difference of two matrices. It's a formal combination of two matrices. So proper way to write it would be to put them in square brackets or something.
Is 2, right?
Sorry? Well, this can be any weight. It doesn't matter. But actually for his methods, so his method works, so this construction works for k greater than 2. But well, I mean, it can be fixed, but then there's lots of other problems that arise. So let's just do the easy case. And I'll just call, so I will drop this square bracket notation and let me just call this matrix. So A is a matrix T squared and B is a matrix maybe ST minus 2. ST minus 2S. So it's just the upper triangular and the lower triangular matrix. So these are the two generators for the group gamma 2. So the solution is a one-liner, but it's kind of very tricky one-liner. So there is a way to write the solution to the system directly, and it's a sum over some set of matrices in, well, so let's call it S for Steuer. Of minus phi, so this phi here, acted on in weight k by gamma. So now, so the only thing that I have to say is what the set of matrices is, and there's two descriptions. So it's either, so it's a set of matrices of the form, so you can describe it in words. So it's b to some power e1, then a to some power f1, then e to some power e2, a to the power f2, and so on. And so you end with e to the power en, a to the power fn. And the conditions are, so e1 up to en are just non-zero integers. f1 up to fn minus 1 are also non-zero integers. And fn is just any integer. And n goes from 1 to infinity. Okay. So and this is a combinatorial exercise. So if you just write this sum formally and see like what happens when you take f and then slash it with a and take the difference, everything just cancels out in pairs. So you just get cancellation. And when you do it with b, you get everything cancels except one term, which gives you this phi. So it's a simple combinatorial exercise, although it's not. I mean, it requires a little bit of thought. But the nice thing is this set of matrices you actually can describe by inequalities. So it's matrices A, B, C, D in the group gamma 2, such that, let me do it correctly. So it's such that absolute value of A is less than absolute value of C, and absolute value of D is less than absolute value of D. So and again, so both claims are kind of not very difficult exercise about 2x2 matrices. I mean, the proving that these two sets are equal is a little bit trickier, but it's yes.
The set S is not all the possible words in the letters.
Not all the possible words. So you have to start with a non-zero multiple of like power of b.
Ah, okay. Yeah.
And but you end in either b or a. So yeah.
So basically, it's b times all the three.
Yeah, it's a non-zero. Well, you have to be a bit careful because it might cancel with the thing you multiply by. So you don't want this first b to cancel. Right. And that actually, so there's this asymmetry. So you want everything to cancel with respect to multiplying by a on the right. And that you see because of this fn is arbitrary integer. So just any two things appear once with a minus sign and once with a plus sign. But when you do it with b, some things, there's one term which doesn't pair up with anything else. Okay. So it's a very nice construction. And so it is related to some, so it's not in a sense completely new. So it's related to some combinatorial constructions related to, there's a so-called Meyer's theorem about Selberg zeta function, and there's a construction for PSL to Z which is very similar, and one can relate the two constructions. But it's a very nice way to do. So it's better construction than the one that Knopp used, in the sense that you don't have to do like any, well, you don't have to divide by anything, and then you don't have this problem with making meromorphic things holomorphic. So this directly works. So the only problem, it converges when k is greater than 2, and otherwise you have to do more work. And so you can make it work for other ways, but it's problematic. So this is, I just wanted to mention it. I'm not going to use that actually. So there's two other ways of proving interpolation, or constructing modular integrals, which in this case are equivalent. So let me describe an approach which I called, well, guessing. And if you read Marina's first paper on the sphere packing problem, that's more or less what you would get out of that. So it's a very brilliant guess. It's a construction that seems to come out of nowhere, and it works. You just check every property directly, but you don't really see, well, unless you know something else, you don't really see where it comes from. So let me just describe this approach. Or, I mean, it's not. So the next approach will actually explain where the guessing comes from. So we want, and I will actually switch back to the original problem, so not this modular integral business. So we want a formula of this type, an hat of x f hat of square n. And let's so let's believe for the moment that this is optimal. So this basically there is a unique, for each value of x, there is a unique formula of this type. So unique sets of coefficients. So for each x, there are unique sequences a and x, and starting from 1, and hat x, and starting from 1, that make this work. So in particular, if you plug in the function f to be one of these functions an or an hat appearing there, if you also believe that these are also Schwarz functions, so this shows that an, they have this kind of delta function, like interpolation property on the set of square roots. So it's just delta nm for nm for any nm greater than or equal to 1. And an hat of square root m are equal to 0 for all nm greater than or equal to 1. So that's just what you get if you assume that this thing is unique. Because if you plug in x to be one of these numbers appearing on the right, there is one obvious formula which does the job. So if this thing behaves very nicely. So now let's try to solve this problem. So, and that's where the guessing comes from, it comes into play. So it's very hard to understand why this works unless you actually, unless you've seen the third method, which I'll explain right after this. So you basically, there's some kind of technical thing which the problem becomes easier if you just symmetrize. So you instead look at Fourier invariant and anti-invariant functions. And what you do is you write this as an integral. So I'll write from -1 to 1, but it's not really an integral over the real line of something of z times e to z by I z absolute values x squared dz. And so there will be two things we want from this expression here. So first of all, let me tell you what the integral is. What is the actual curve of integration? So it's a semicircle connecting -1 and 1. So it's useful. So actually, the next thing you do, you actually deform this semicircle, but it's important for one of the two properties. The first thing that we want is let me call this bn of x.
So Danylo, I missed this. So where does the GN now come from?
Yeah, so it's not, I haven't explained it yet. So it's an ansatz. So you do this.
Okay, so at the moment it's an ansatz.
Yeah, it's just something, and then you work out what properties it should have so that for everything
Okay,
works.
so can you slide back a bit? So you want
So we want this thing. So
okay,
this is one of the two
you
properties.
basically want n of square root n.
Is G for guessing?
Yeah, I didn't realize that. Yes, it is for guessing, indeed. I mean, usually the problem is whenever I'm defining a new function, it is either f, g, or h, and then there's too many functions and too few letters.
So why do you want this guess one? I mean, these properties are related to the distances somehow.
So guess one. So I kind of explained it in words. So if you look at this formula here, and let's assume that this is like unique. So there's for each x, there's only one way to do it. Well, if you plug x equals f of square root n, well, the obvious way to do is to write f of f squared n is equal to f of square root n. And then this means that this at the point square root n, these functions have this interpolation property 1. So, but again, so it's a terrible method because you have to kind of assume a lot of nice things and then just believe that it works in the end. But that's what we're trying to do. So we're trying to construct functions which satisfy 1. And so the functions Bn, they also have this delta function property, but they're also Fourier invariant functions. So first we want Bn of square root n to be a delta function of these 2 points. So it's just the Kronecker delta, not the Dirac delta. And then 2, we want Bn to be Fourier invariant. So this guess function Gn, well, so first of all, I want it to be holomorphic so that the passive integration doesn't really matter. And it will be convenient to have 2 passes. So 2 pass. So one is the semicircle and the other is a rectangular pass. So one of them we'll use to prove this thing. So this is the semicircle, and for this delta function property, we'll use the square. So for the semicircle, it's actually kind of easy. You just apply Fourier transform to the integral formally. So so Pn hat of x is equal to the integral from -1 GNC. And so I have to say which dimension we're working in. So let's say that dimension 4. So that would be minus tau to the power -2 e to the pi I -1 over tau squared. Tau with the tau is e. It's probably c. So this is also c. And then you change variable, so z goes to -1 over z, and so this thing is equal to so integral from -1 to 1. I mean, maybe up to sign errors. Gn of -1 over c, e to the pi I z squared. So we again get an expression of the same type. So let's just postulate. So for Fourier transform, so okay, just different conditions. So Gn of c should be equal to Gn of -1 over c. So that's just, and that will give us the Fourier invariance.
So the Bn's are now the Fourier coefficients of the G, or no?
So Bn is this kind of finite integral transform of G. And then we'll write 2 properties for G, which actually will tell us that G is a modular form, a modular, like weakly holomorphic modular form.
And right now, is this all a warm-up case for the more general version where you have the derivatives?
Yeah. So I'll explain what one needs to do to fix everything there.
Right.
Yes. Although I will be much less detailed because it's there's a lot of technical issues which arise. So, but this case gives a very good indication of all the tools that are used.
Thanks.
and the second thing, so if you now use instead of circle, we use this contour. And that's, let's see what it tells. So if you plug in square root m, so bn square root m, it's integral, I mean, over this picture now, of gn of z. And now, because it's square root of m, so it's e to the by I mz. See, so it looks like a Fourier coefficient, and in fact, so if you make gn to periodic, it is a Fourier coefficient because the contributions from these two sides cancel out. So that's what we do, and then bn of square root m is the coefficient of minus q to the power minus m over 2 in G. So it's just a coefficient, Fourier coefficient. And so, well, with these two properties, you kind of see that Gn is a modular form for some group, which is a group generated. So Gn is a modular function, in fact, so it's weight 0. For the group generated by t squared and s. This is what we sometimes call the theta group. And so the only thing, so we want this to be a delta function, so we have to find a Gn with Fourier expansion starting with q to the minus n over 2 plus well, plus the next term should, so there's only one negative term, and the next term should be C0 plus C1 Q. And there's a simple, simple exercise to show that there is a unique such function for every n, and that's the one that you use. And so, well, this is all nice. So you get a construction of a sequence of functions which have this almost what we want, so this interpolation property. Then you have to prove that actually then if you plug everything into like a series and everything actually gives you an interpolation formula that works for all functions. And that kind of, I mean, it's all backwards. So you can do this, and that's actually the way we did it originally. And in the end, so let me tell you the better way. So then, I mean, then you kind of plug in expressions for an hat, and then hope that everything works. So a lot of work. So the real good way of doing this is to transform it into something called the Riemann-Hilbert problem. Although this is a very, very simple Riemann-Hilbert problem. So people who actually study these things, they will probably laugh. So so let me come back to the modular integral formulation. So we want a function which is 2 periodic. So 1 minus t squared is 0. And so instead of having this two functions, so let me just do the same symmetrization business with Fourier transform. So I will have, instead of the condition for this st square S matrix, I will have a condition well, with S matrix. This will be something of this type. So that's what you get when you symmetrize the problem with respect to Fourier transform. So you get, again, a modular cocycle problem, but for this group gamma theta. So modular integral for gamma theta. And so, and this is in weight k. So there's two steps. So first is there's a way to reduce it to weight 0. And the way to do it is actually kind of, well, it's very simple, but it may look a bit dangerous. So you divide it by the power of the theta function. So this leads to a different problem. So this gives, so weight goes from k to weight 0. But phi also changes. So phi you also divide by theta. It's power k over 2. And this it's a little bit. I mean, it requires some convincing to see that it actually works. So, but it's direct calculation. And the problem is, well, it kind of. So the nice thing about theta, it doesn't vanish in the upper half plane, so you don't introduce poles, but you do introduce poles on the boundary. So it's there is some danger involved in this operation, but let's just ignore that completely. And so let's say k equals 0 from the start. And let's see what, so I'll draw a picture. So maybe if you like visualizing things, it will help understand what's going on. So we want two equations now in weight 0. So it just means, so we have a function which satisfies this. And we have a function, I mean, it also satisfies kind of another functional equation. Well, 5 tau minus 5 minus 1. And so let me draw a picture of what's going on. So a fundamental domain for the group gamma theta, it's it's similar to other fundamental domains I've drawn before. So it's this strip without a semicircle, but now you use the same semicircle as in this gas construction. So let's call this f theta. And so there's a point I here and the 2 points -1, 1. And so what you do, so you want to come up with a holomorphic function on this domain, which has some boundary conditions. So it kind of, if you glue the things together, you want some matching conditions on these two parts of the boundary. And so this is the tau periodicity. So this is t squared. And then this, so this S condition, well, this S condition, it's matching 2 points here. So on the semicircle. So if you map this thing conformally, and I'll just call this function that does this conformal map J, and so it won't matter too much for now what it is, but it's lambda times 1 minus lambda over times 4. So it's this lambda invariant that I introduced at some point. So you map it to a slit plane. So you map point 1 to 0, point I to 1, and then, so yeah, let me do some colors maybe. So this, the vertical lines you map to, let me see, to the left. And then the semicircle, the two parts of the semicircle, you map to the right. Maybe let me do it the other way around. Just a second. I want to do this to be this thing, and then the third. So the third part of the line. So it's actually not a part of the boundary in the original picture. So it's this line, and it's mapped to this ray here. Okay, so now there's like 2 bits, I guess 1 and 2, and I think it's preserving the orientation. If I'm wrong, it doesn't really matter. So, okay, so let's see what happens. So now, what we want to do is we just want to solve the same problem, but in these coordinates. And then the problem becomes, so here across this dashed line, there's nothing. So it's just holomorphic. So we want a function which is holomorphic. And it's in the image of the domain, it's holomorphic. And actually, so this matching condition, periodicity condition along this orange-red part, it's telling you that here it's also holomorphic. So it's holomorphic everywhere except along this interval. And along this interval, this condition is just a jump condition. So you want, when you cross this interval, you pick up the value of phi at the corresponding point. And so you get a kind of jump problem. So you want like, let me call this some other letter, phi of z is f of this inverse map. So we want phi is holomorphic in C minus the interval 0, 1. And when you approach this interval from above and from below, you pick up so this thing should converge to up to some constant multiple, it should converge to the value of phi. X. Yeah, and so again, so it's a little bit more tricky, but if you kind of ignore the difficulty in defining this, you just call this W of X. And so there's a very simple, I mean, I don't know, it's maybe more than 100 years old solution to this problem. So it's so-called Zachodzky, yes, Zachodzky-Primelli formula. Yes.
But plus I0 minus I0, you just mean the limits.
Yeah, so it's right above and right below, yes. So, but really it's just the values of phi at these 2 points in here. And not sure if I'm actually spelling it correctly, but yeah, in any case, it's not very accurate. So there's a formula, which is just, I mean, you use the Cauchy kernel. So this phi is 1 over 2 pi I times the integral over this interval of W of t divided by t minus z. And so what's important here is this way double is actually holomorphic. So this solution, it extends holomorphically from just this fundamental domain everywhere else by reflections. So that's the good way of solving the problem. And what's nice, so if you translate it back, back into the coordinates on the upper half plane, so back into H, we get an integral kernel representation for the functions we're looking for. So you get f of x. So the full generating series is an integral, at least, sorry, f of tau. So fx of tau is an integral with respect to some kernel, which is just a pullback of the Cauchy kernel to the upper half plane by this conformal map. Of this thing. So I'm just doing several steps at once, but I'm just I'll explain it maybe a little bit. So
that was the rewriting of the W. Or
yeah, so this is now for this special case when this phi is the one that comes from the interpolation problem. I mean, in general, you would have phi here.
Right.
Yeah. And this thing is something that's actually people also consider in modular form series as something that modular or automorphic Green's kernel, or Green's function. So it has some, I mean, there's a way to define it kind of more systematically without doing all this conformal maps. But so there's some characterization of this thing purely in terms of upper plane. Am I doing on time?
it's 37, so it's supposed to. We are supposed to finish at 1 p.m.
Okay, that's good.
I don't
That's
know.
good. So this
With
is.
breaks, if you want to do breaks or not.
I'll do a break, but let me
But
move
so
to.
initially the break was from 50 to 12, 11:50 to 12, but we can
Okay,
move it around.
that sounds good. We can make a break in 10 minutes. So okay, so now let me do the other thing that I promised. So explain how the how this formula with derivatives works. So this, because it's important. So I mean, this
Can I
actually.
take time out to make a commercial?
Oh, okay. Yes.
It's for complex variables, classical complex variables. I mean, this is really the beauty of it. You know, it's classical subject. I was brought up on it, so this is my first love. And it's wonderful to see this come in. You know, it's still alive. It's really important in this problem. And, you know, I really urge you to take complex variables or complex analysis if you haven't had a course in advanced courses. It's a beautiful subject, clearly applicable.
Oh, yes.
Okay,
yes.
sorry.
I fully support this. Yes. Yes.
Too excited here.
Okay. So I'll spend like an infinitesimal amount of time discussing the actually important case, because it's kind of all the techniques work, but they become much uglier. So unfortunately, somehow this toy problem is much nicer, but the one that we care about is well, as an application. So the toy problem, we don't really know how to apply it to any geometric question. So let's look at the square root 2n formula. So what do we need to change? Well, we play the same game, so we just prove it for a collection of Gaussians again. And I won't do the actual rewriting of the expression that you get. So in the end, I'll just write the system of equations that you need to solve. So you need to solve the following system of equations. So again, it's Gaussian. You want to express in terms of two kind of generating series. Let's just say we're working R2K so that I don't have to write D over 2. So and so this is the condition. It's basically the same thing. It's always the same thing when you try to make this Fourier like two generating series, one for the Fourier transform, one for the functions themselves. And it's just because of the Gaussian's behavior under Fourier transform. But now the point is, so now we have a different set of points, and we have like this derivative business coming in. So instead of 2 periodicity, we get a difference equation of over 2. So the second difference should be 0 for the two functions g, f, and g. And again, there's also the growth condition, so f and g should be in this class B. But somehow, like this is the less important detail. And so the problem is, so how to translate it into something like a modular integral question. So this directly doesn't work. I mean, it's a different problem. And there may be other approaches to this. In fact, in the paper in universal optimality, we kind of avoid a lot of vector valued discussions. But let me just, so there is a trick. So you vectorize the problem, make it, instead of a scalar problem, you make it 6-dimensional, and it becomes worse, but it becomes better. So the worst thing is you have to work with 6-dimensional representations, but the better thing, it becomes a modular integral question. So you take a collection of functions instead of one function, and it's this collection. And the reason, so this looks like somewhat complicated. So the nice thing about this vector is if you use star, so using star, you can rewrite what happens. Okay, you can rewrite f of tau plus 1 and f of minus 1 over tau, and it's a very boring but necessary calculation. So you can rewrite these in terms of original f of tau. In terms of f of tau. So this curly f, it's under modular group PSL to Z. You know how it changes, except that it changes not like in the way we discussed before, but it just you multiply it by something. It's actually a matrix that you have to multiply this vector by. And let me, I don't know if, well, since I copied them down. So what happens is this vector transforms as follows. So now it's actually a cocycle where both components are non-zero. And I'll write, I don't know if I want to write these matrices, let me think. Is psi s of t of tau. And so now these AT and AS are some 6 by 6 matrices. And so let me maybe write them out, or at least one of them. So it's mostly 0, except few non-zero entries. 1, 2, minus 1, 2, 1, and 1 here. So everything that I'm not writing is 0. And hopefully it is 6 by 6. Good. Yeah. So and AS is actually even, well, it's easier. So it's just 1 anti-diagonal. Everything else is 0. And so it's kind of boring exercise that you actually check that this works. You just have to use these functional equations many times and see if it's close.
These matrices, do they operate on a couple of was it 3 or 6 functions?
So you operate on the 6 on C6, yeah. And so you actually get the 6 couple of functions. Yeah. And now instead of looking at modular forms with values in C, you look at modular like functions with values in C6, which transform this way. Right. And so this double star.
So the psi's are also 6-dimensional.
Yeah, psi's are also, and they're all, yes, psi's, I can also write them down. So they're also mostly 0, but they're not. So it's 2 times phi slash s minus phi slash t inverse s 0, 0 to phi. And I mean, there's probably no sense in copying what I'm writing because it might be, might be some mistakes. But just to give you some impression of what this looks like. So again, these are like 6-dimensional vectors, and so you get a vector valued modular integral problem. So you get vector valued modular integral problem double star. And so the nice thing about it is, in a sense, it's the way to solve it is the same as before. So you just map it conformally onto a slit plane, and you use something which replaces the Sochotsky-Plimelli formula for this representation that you compass. And it's kind of, it requires a lot of work. So the nice, I mean, there's strange thing about this representation. It just comes from the problem. And in principle, so one nasty thing about representations of PSL to Z are kind of a meaningless object to study because it's just a pair of 2 matrices with 1 of order 2 and 1 of order 3 with no other conditions. So they're very wild. So in general, they have no nice theory. But this particular representation is actually nice. So first of all, when you start like looking at matrices for bigger, so elements with large norm in PSL2Z, the norm of the matrix, the 6 by 6 matrix doesn't blow up. So it's not, it could grow exponentially very easily, but this doesn't happen. So there's something about, so this is a representation of polynomial growth. So representation of polynomial growth, meaning that so this representation at PSL2Z to GL6Z. So if you look at law of gamma, you look at Frobenius norm, for example, it's bounded, so it's bounded by some power of the norm, Frobenius norm of the matrix gamma. Or somehow. And that, so that more or less is the only thing that you need for this whole theory to work well. And so, but if you think about the problem, it kind of is arbitrary. So you just come up with these two matrices, they just come from the interpolation problem. And for some reason, they actually are nice. So they you do get a representation which is not wild. Okay, and so the problem becomes to the detailed work. So So you have to describe what modular forms are for this representation. So describe modular forms. Representation rho, and I haven't quite defined what it means, but more or less you can guess it's just so functions which transform with respect to SL2Z using this representation. And this, so I'll just drop all the details so you come up with, so first of all, this representation splits. So this 6D rep splits into two 3D. And one of these is very nice, and the other is less nice. So one of them is a symmetric square of PSL2Z. So it's actually given by polynomial. So it's a polynomial representation. So symmetric square. So you just think of PSL2Z acts naturally on a two-dimensional space, and it also acts in quadratic polynomials in that space. So that's the representation. And there is a nice result by, if I don't mistake the name, yeah, by Kaneko, so theorem of Kaneko and Nagatomo, that symmetric powers of the PSL2Z, so vector valued modular forms are the same as, up to some linear transformation, the same as quasi-modular forms.
So they are vector valued of dimension 6.
So this part is dimension 3, the symmetric square part.
Yeah, but in the first line.
The whole thing is dimension 6. So this thing, so sim to the power k is the same as quasi-modular, and I'm like stating it very roughly. And what is quasi-modular? Well, for the purposes of this course, so quasi-modular, I won't give the proper definition, but it just means a polynomial in this non-modular form G2 with coefficients that are modular forms. So in other words, the only thing that you need to know that this representation for this, you already know what the modular forms are. So half the problem is done, and the other half is, so you just have to work it out. So this involves logarithm of the lambda invariant. So that thing appears in the description of modular forms for the other part. And so once you do everything that you have to do for like to work out the explicit formulas, so and plug this into the problem that you start with, so you get a formula for the magic function, for the candidate for the magic function. that's subordinated by Gaussian with parameter pi alpha. And the formula is nice. So it's reminiscent of what Marina found for the sphere packing problem. I mean, it's essentially it's the same formula, but with an integral kernel. And so this kernel is an absolutely terrible special function, probably the most terrible special function I ever had to work with. So it's completely explicit, and there's no meaningful structure to it other than it's like a long expression that you can write down. And so explicit, but to the level of our understanding is meaningless. So there's nothing special that we can use about it to make our life easier. But what we have to prove, so we want to prove this like majorization inequality and the positive definiteness for the candidate. And so at some point you have to prove that it's actually negative on the imaginary axis. So k of alpha it is negative. This, I mean, it's actually a stronger statement, but this implies universal optimality.
Just a moment. So basically, to obtain the K, you proceed like in the toy model.
Yeah, you proceed like in a toy model, but you have to do like vector valued things, and in the end,
so you do this thing with a J and the slit, for example. And
yes.
then,
so you write down an analog of the Sochotsky-Primelli formula for that, but it's vector valued, so it's a lot of I wouldn't say fun, but it's a lot of work.
But is it a formula with a 2D part and then a matrix part, like a tensorized together?
No, it actually is like vector valued, but in the end we land in a scalar valued part of that representation, and that's the one that we care about. So this is actually a scalar valued kernel. So it's just a function in two variables. We can write it down, and in 8 dimension it takes like a page to write down explicitly what it is. So you can write it in terms of elliptic functions of like e and k and logarithms and polynomials. It's like when I give talks, I sometimes show this function just to scare people. But so it's perfectly explicit, and then it's actually a very long technical part of our paper. Some of it is very computational to actually prove this inequality, which. It's a separate topic, so I don't want to discuss it because it's very, very hard. And we don't have a good conceptual explanation of why this has to be true. So it's in the end, you just do some calculations and it works. And I would love to have some explanation, say like if you know that local optimality of E8 implies this inequality or something of the more conceptual flavor. But that we don't have. So we just have a proof that at a certain point, everything works very nicely and conceptually up until the point where you actually have to prove universal optimality. And then you just have to prove this inequality, and there's no conceptual reason why it should be true. Okay, so, and let me make a small break, and then I'll move on to this speculatory part of the talk, and then maybe we have some speculatory. So, and then, but maybe also if someone has questions.
Any questions?
Yes, so the big picture of what you spoke about over the last hour,
Yes.
you said these were 3 different routes to the Fourier interpolation.
Sorry,
3 different paths to the formula.
Oh, 3 different paths. Well, not really. So, okay, so the original path is to actually use Knopf's result, which you can make it work, but it's not worth it. So then the second thing was this discovery of Martin Stoller. There's a nice Poincare series which directly solves it, and so that's one. Well, the second way, and then the guessing method is actually not a method. So it's, I mean, you can employ it if you're a genius, but I'm not. But the good thing is the third method works, and it most works for both problems, for the square root n case and the square root 2n case. And just
is this the method you use in the paper?
This contour integral business is the method we actually use. Although we don't. I mean, I don't think we actually explain this connection with the Riemann-Hilbert problems, this jump condition. So we don't actually make this picture in the paper. We just work out all the details on the H side, and that's good enough. But I think for to explain how this actually works, this is much better because we transform it into a problem that people solved 100 years ago already.
But then you have to do it with 12 equations instead of 2. Right.
Yeah.
So that's why maybe you don't have a picture.
Yeah. So there's a way to make kind of avoid doing this vector valued computation. You can keep things scalar valued, but then it becomes more esoteric. So I think this is better for explaining how it works. Yeah. Okay, so let's make a break.
Let's make a short break, and then we come back in maybe. Can it be 5 minutes?
As much as you want, or as little as you want.
Let's do 5 minutes, so then we are relaxed at the end.
Yeah, and then I will slow down. So there's not much more I can tell you, and I will tell you not that much. Okay. So there's just a few things I want to mention. So some of it kind of points in the direction of what one needs to do for the A2 case for this type of strategy to work. But there's something kind of interesting. So there's a general problem, or a collection of problems that I want to just formulate. So it's something that's now it's called Fourier uniqueness pairs. And it's a very, very young subject, which more or less appeared out of this whole story with universal optimality, and interpolation. And hopefully it will develop into an actual theory. So there's let me just formulate something which looks similar to what we were proving previously, but a much more general formulation. So we have a collection of two sequences of numbers. So going to infinity, and so lambdas and mu's. Mu n's going off to infinity. And so the question that we're interested in is, it's like a generalization of the square root n formulas. So let's consider the map from radial Schwartz functions on RT to spaces of sequences. So the values of f at lambda n's, and the values of the Fourier transform mu n's. And so the Fourier uniqueness pair, so lambda and mu is a Fourier uniqueness pair. So let's call this map phi. If phi is injective. So in other words, when the reconstruction can work from this data, and then you can impose some stronger conditions. So tight if phi is surjective onto spaces of sequences of numbers of rapid decay. Surjective. Well, and sometimes maybe it's a little bit weaker, but maybe almost surjective up to some finite dimensional space of relations. Or almost surjective is also fine. So in other words, we want something like a Fredholm operator. So this tight Fourier uniqueness pair business is kind of it's important for the whole story with E8 and the Leach lattice. And surprisingly, well, maybe not surprisingly, we have very few examples actually of uniqueness pairs which are tight. And until recently, we had very few examples of uniqueness pairs in general. But there's been some.
This is the case where the band-limited function don't count.
Yeah, so I'm writing here non-strict inequalities, but really I want most of them to be strict. So maybe I'm just writing it to have possibility of having multiplicities. So if you have two numbers coinciding, that just means you also add the derivatives there.
This is because the Mueller go to infinity.
Yeah, they go off to infinity. In fact, if you just pose strict inequalities, it's a perfectly good problem. But you also want to include this double root interpolation. So, so there's some condition, some heuristic condition, which heuristic is something that looks like an uncertainty principle. So the heuristic is the following. So if you define the counting numbers and lambda of x is just a number of n such that lambda n is less than or equal to x. The same thing for n mu of x. So the condition that they should satisfy for this to be a uniqueness pair, and this is not a rigorous result. So this is in some cases it is rigorous. So n lambda of w plus n mu of t should be bigger than or equal to 2wt. Well, for all things greater than 1. And this is very, very imprecise because it's not a real theorem, it's just a heuristic. So it might be a little bit weaker than that, maybe minus some power of logarithm of wt, possibly, or something else. So it's just to give you some indication of how these sequences should grow. And if this thing is almost tight, so this is if the one of the sequence is fixed, there is a canonical choice for the n mu of, so for the second function n mu of tau n mu of t that makes this inequality work, and this is a so-called convex duality. So it's, or sometimes called Legendre transform. So there's a transform coming from one. So I'm being very vague. So optimal n mu of tau is the convex dual of n mu and lambda of w. So just to give you an example that we were talking about all this time is when, well, lambda and mu are square roots, then both things and lambda w is w squared and mu is t squared, and this is just the inequality that you all know. And in fact, I mean, this is so this x squared is self-dual under this convex duality transform. And one can do other things. So for example, so if you're saying lambda is a sequence of other powers, c times n to the alpha, and let's say mu is a sequence of d times n to the beta from 0 to infinity, and alpha plus beta is 1. Then so this optimality comes in. So I guess tight case is when the product 2 times CD is equal to this number. So you can work out what is the best, what this inequality looks like, and it actually tells you this condition. And so, like I said, until recently we had almost no examples of these Fourier uniqueness pairs, but there was a very nice work, which, as far as I know, still hasn't been made available by Nazarov and Sodin, and now I think it's also another person joined it, and Kulikov. So they proved that if you're away from this tight case, then they actually, so what the heuristic that I described is actually precise.
It's in progress or something.
there is something circulating, but it's not a preprint. So it's but I've read the proof. It's perfectly correct. I mean, if you know these people, you know that they're amazing.
Careful.
Yeah, very careful, and then they're excellent analysts. So in this case, there is a uniqueness, and interpolation formulas coming with them. And the only problem is there's too many interpolation formulas. There's not one that you can pick, which is nice, but there is many formulas. And so actually lots of them. And so in the opposite case, when the constants are bigger than this critical case, then there's non-uniqueness. And in fact, again, there's lots of functions which vanish on these sequences. So it's infinite dimensional spaces in the kernel. It's space of F vanishing on both sides. Well, and so as long as you stay away from this critical case, actually what they did is very robust. It worked. It doesn't require these sequences to be so regular. They can be kind of, they just have to grow this way, and they have to have not too many clusters. And so this kind of explains the whole thing very well. So let me now tell you what it tells you about the A2 case and why it's different. So even in the case when alpha and betas are 1/2, so in this case, we actually have a complete picture for these sequences. So we combine our result with Marina with their result in the non-critical cases. So you completely know which ones are uniqueness pairs and which ones are not. So let's now. So what the result is saying is if you have fewer points, so asymptotically fewer points than in the square root n case, then well, there are plenty of functions which vanish on these sequences. Vanishing on both sides. I'm getting a little bit vague, but let me just explain where I'm leading. Both sides. So let's come back to the Kohn-Kummer optimization problem. So Kohn-Kummer, well, in 1D, you had the problem. So there's inequalities and then there's equality constraints. So this complementary slackness phenomenon. So the equality constraints are more or less well, something. So f and f prime, you know what the values are, and the Fourier transform is 0 at integers. In 8D and 24D, this is the case I've been talking about today. Well, before as well. So you get the square root 2m. Something, and then f hat vanished to second order. And this is tight, and this is everything. So the problem gives us exactly the amount of information we need to solve it, and not anything else. So the remaining case, the 2D case, is very nasty, and of course you all know it. But so it gives us some information. And this information is plentiful enough so that you can't come up with simple functions which satisfy it, and it's not enough to make it unique. So now with this like result of Nazarov and Sodin, we know well quite a bit how badly this non-uniqueness happens. But let me tell you what the conditions are. So the conditions that you get are the values at these points, and something with derivative, equals something coming from the Gaussians, and the same business, sorry, not equal, but of course, so here, fix it. And something with derivatives with the same points for the Fourier transform, it should vanish to second order. And now if you look at the sequence, so the sequence of numbers, A, B, integers, just the sequence of the set of values of this quadratic form, well, actually, somewhere, so 0, 1, 3, 4, 7, 9, 12, 13, 16, 21, 25, 27, and I'll stop here. So there's a few properties of the sequence. So first of all, there's no way to describe it in any closed form. So it's a very, I mean, you can write down arithmetic conditions for it, but it's hard to work with them. So it's something about the primes that divide these numbers. But the bad thing, well, and what makes a 2D case kind of fall outside this nice sequence of other dimensions is that, well, the number, so number of points, let's call this set S, number of n in S n less than or equal to x. So this is asymptotically c times x over square root of logarithm of x. So you actually get density of numbers which is 0. So 0% of integers land in this sequence. Unlike the 8 and 24 dimensional case where it was exactly half, so it's all even.
There are much more.
They're much richer, and so because of this, so Nazarov, Sodin, Kulikov, well, result. So their result implies that there's a lot of functions which actually solve the interpolation problem. So there's a lot of candidates. And the whole strategy in the 8 and 24 dimensional case kind of hinged on the fact that there was just one function that got given to us, and we just had to prove an inequality in the end. And here, so the real problem, in my opinion, so what is the right definition of what the magic function should have? What is the right property of the magic function? What is the right definition of magic functions in 2D? And so even if you impose inequalities, we have numerically lots of examples which are quite different. So even the magic functions in the definition of Cohen-Kummer, there's plenty of, and we expect them to be infinite dimensional, well, convex, like affine spaces, right? I guess convex spaces. And so, but the 1D case was kind of similar, right? So we had very little information in the 1D case, but then you could still do everything. So what one possible approach is, so add more vanishing on the Fourier side. And that's the way the 1D case worked. And so the real problem is to find a natural sequence of numbers. So is there a natural sequence of numbers? I don't know, I'll call them mu n, same way as before, containing the set of integers S, or the set of numbers, like the square roots of these, such that it has, so the number of mu n less than x would grow like x square roots like x with some constant. And that's kind of, so if you can figure out what this should be, you can try studying the space of functions whose Fourier transform vanishes in the sequence. So, well, unfortunately, to this moment, we don't know what this should be. So there's some other ways of fixing this non-uniqueness. So, yeah.
Just to understand the message you are sending, yeah.
Yes.
You are telling. So basically, the Nazarov sorting Rico says that actually you get a lot of possible choices.
Yeah, it's not even a lot. It's too much choice. Yes.
Like many choices where you can get a unique solution to these equations.
No. So they're saying there's infinitely. So you look at these equations here. There's infinitely many infinite dimensional spaces of functions which have all these properties.
Which solution to the equations.
Yes, to the equations here.
Yeah. So they have infinitely many solutions, but then I'm lost. So isn't it enough to have just one solution?
No. This has nothing to. So we actually care about the inequalities in the optimal.
Right. Okay.
And so there's no way. So their construction is not.
So to have many solutions.
There's no way to control the inequalities.
Because you don't know that only the function that so you would like to impose maybe like second derivatives or something like that. I don't know.
Even more derivatives, possibly. So the question is: this is an incomplete set of conditions for. So if you believe that there's one super nice magic function, we don't know what properties it should have in addition to these. And if there's many of them, we don't have a way of constructing like, I don't know, proving that the space is non-empty. So it's that's the problem. And so the way
all the many solutions, you would like to find one such that all the duality argument goes through. Yeah. And this is the difficulty here because you don't have uniqueness and you cannot play with one function.
So and this kind of ties back into the problem with 8 and 24D case where we don't have a conceptual reason why universal optimality holds. It's just that the only possible function that could work does work. So yeah. And actually I'm more or less finished. So maybe there's some questions that I yes. Okay. So let me just stop here and then maybe I can comment some more if there are some questions about the situation.
Yeah, so are there any questions? More questions?
So you've got two conditions, positive definiteness and staying level. You have any conditions that kind of auxiliary conditions that prove one or the other, or they just both? Right now, there's. So if you wanted to just first of all ensure positive definiteness, then can you think about it as conditions that will that a little easier to work with?
So the problem is like if you forget about these complementary slackness conditions on the optimal function, there's of course a lot more flexibility now. So you can come up with positive definite functions which lie below the Gaussians. But then, as far as I know, there's no good way of making them converge to something which is optimal. And you know, the optimal solution has this like vanishing on this strange sequence of numbers. So, so this Nazarov sodium business, it helps you construct functions like the solutions to this equality constraints. But the way it does it, there's no control you have over any like inequalities. So it's destroyed completely. So we were kind of trying to do something with that in that direction, but there's basically, it doesn't seem like it's going to work. So like I said, so it seems like unless there's some completely different approach, which I mean, there could be many, but if you want to make this thing work like similar to the 8 and 24D case, you actually have to figure out what other conditions to impose on the magic function, or find some other way to prove that the space is non-empty. But yeah. So of course, I'm not saying much that you didn't know before, but
So any more questions?
yes, I should also mention. So I'm saying, so I'm forgetting some name here. So there was, so this particular the non-uniqueness question was actually solved separately by I think his name is Nasser Sardari. But it was in a very special case that we actually asked in the universal optimality paper. So this the Nazarov-Sorin result is a lot more robust. So
So since there are no more questions, I'm going to stop the recording and